And we have another integral. So the previous video that I did was actually recorded the previous week. So, this week I actually had time to make another integral, a bit more a complicated one, and this is sort of, like your normal weekend video, and the other one, which was the casual one, was sort of the extra. So the casual ones are gonna be like extra content. They're not gonna block the way, I hope, of the normal content that we usually do, which is the incredibly difficult integrals that look actually insane. But yeah. So that would mean I hope that there would be 2 videos coming out this weekend, and then whenever I do one of those casual ones, it'll be 2 videos every weekend. But that depends. So here we go. We have here quite a new type of integral. We haven't really seen this sort of stuff. But what I want to do with this first is I'm going to factor out a 1 over the square root of x times 1 minus x in the denominator. And so we get that this is equal to the integral from 0 to 1. I'm actually going to start to write a little bit smaller here because there's a lot of steps and I don't know if I can fit it into one whiteboard. And my new device that I'm using, I can't pause the recording. So if I press the button, it'll stop the recording altogether, which is a mistake that I made 100 times. Which is only 3 times. We have the square root x times 1 minus x times 1 minus square root x times 1 minus x. And this is actually kind of funny because if you look at it, it's going to be the inside of the radical is x times 1 minus x, and then the denominator is the radical times 1 minus the radical. So there's something fun. Now what we're going to do, we're going to use the Taylor series for this, the geometric series, and then for this one, we're just going to write it in power notation, which is x to the negative 1/2 times 1 minus x to the negative 1/2, so we have an integral from 0 to 1, x to the negative 1/2, 1 minus x to the negative 1/2 as well, and then we have a sum. And it is starting from 0 to infinity, because we have that geometric series. We have square root of x to the n, which is x to the n by 2, and then the same thing with 1 minus x to the n by 2 dx. We can drag this onto the outside, and we can join up these powers inside the integral. So we would get we would get the sum n is equal to 0 to infinity. I hope I'm not writing too small. Can you see that? I think you can. So we have an integral from 0 to 1, and then we have x to the n minus 1 over 2, 1 minus x to the n minus 1 over 2 dx. And this, my friends, is an integral representation of the beta function, which is gamma of x, gamma of x plus y. And we're going to use that. But we're going to notice, and I'm going to switch to my blue pen, because yes, I did buy 2 pens for this video. We have the beta, never mind, this thing has no ink whatsoever. Beta of x, y, is equal to an integral from 0 to 1, x to the, not x because that's already used, t to the x minus 1, 1 minus t to the y minus 1. dt. So here, if we want to turn this into the beta function, the powers have to match. So x minus 1 is n minus 1 over 2. You can add 1 to both sides. We have n minus 1 over 2 plus 1, which is n plus 1 over 2. So we have here, this is equal to the sum, n is equal to 0 to infinity of the beta function of n plus 1 over 2, comma, and then the exact same thing for y, so n plus 1 over 2. Alright, so there is our little series, and I'm going to erase this definition because we now no longer need this, and actually we're going to need something else in just a minute. And that is going to be a different representation of the beta function. It is now beta of xy is equal to 2 times the integral from 0 to pi over 2. there might be easier ways to solve this, but in my solution, I use this representation: sine 2x minus 1 theta cosine 2y minus 1 theta. Theta here. Right, so now we can use this. Now, how can we use this? Well, 2 we can just drag to the outside, so we have here 2 times the sum, and is equal to 0, infinity. And then so we have this other sum. Now, what is n plus 1 over 2 times 2 is n plus 1. Minus 1 is just regular n, 0 to pi over 2, sine, then theta. And then over here, we have, this is going to be the exact same thing. So it's going to be cosine, then theta, d theta. Alright, that's great. We can now swap this order on the condition that it converges, which it does, because sine is always a little smaller than or equal to 1, so it does. Anyway, if we drag that in, this is now a geometric series, so we can use the geometric series formula, and we will get, this equals to 2 times the integral from 0 to pi over 2, 1 minus sine x cosine x dx. And I switched from theta to x here just so it looks a little bit more aesthetically pleasing. And then we'll erase this again. Alright. So now our main and only goal is to solve this integral right here. After which we can just multiply by 2 and we would get the answer. So what we're going to do, we're going to notice that sine x cosine x here, that is the double angle formula of the sine, but divided by 2. So the sine of 2x is 2 sine x cosine x, so we can rewrite this as this equals to 2, the integral from 0 to pi by 2 of 1 minus 1/2 sine of 2x 1 dx. Okay, cool. And then we can multiply top and bottom by 2, so that will cancel this out. And so we get 2 times integral 0 to pi by 4, and pi by 2 over 2 minus sine 2x dx. And now we can use the Weierstrass substitution, which in this case is actually going to be slightly different because we have a 2x here. What would this be? Well, okay, first of all, this 2 and this 2 we can combine 2 and make a 4. Alright, that's better. And now we can make use of the substitution. T is equal to tangent of just x here. And then we can take the arctangent. We have x is equal to arctan t. And then dx will be equal to dt over t squared plus 1. Alright, cool. Now, what we need right now is the sine of 2x. Well, remember that double angle formula we were talking about? Well, we can actually make use of that. And we're going to say the sine of 2x is equal to 2 sine x and the cosine of x. And now, what we're going to do, we're going to divide this by cosine x, and then to make this equal, we're going to have the times by cosine x again to make this cosine squared. Now, sine over cosine, that's just the tangent, so we just have 2 times t, remember t is a tangent, and then for this cosine squared, what we're going to do is we're going to write it as 1 over the secant squared of x. And now we're going to make use of another trick identity. The secant squared is just tangent squared plus 1, and we know that the tangent is this, so we have t squared plus 1. So now we have our representation, and it's time to plug that in. So we would get this equals to 4 times the integral from 0 to pi by 2 of, let's see here, we would have 2 minus 2t over 1 plus t squared, over here, 1 over that, and we can factor out a 2 on the denominator, so that is 1, and this is just regular t, and then with that, this turns into a 2, okay, and then from this one, we have dt over t squared plus 1, this and that cancel in theory, and so we would get So what do we get here? So 1 times this minus the regular t. So essentially we have, you know what, we're actually gonna, we'll keep this because this is our substitution. This is equal to 2 times integral 0 to pi. I actually messed up that, because if we're gonna plug in the right bounds, this thing, the tangent of pi by 2 should be infinity. I did not notice that. So we have integral from 0 to infinity, and then we have t squared plus 1 over here, so t squared, and then this is gonna be minus t plus 1. Okay, cool. And then now we just have a relatively basic integral. You can start by completing the square. So how we do that, we're going to notice t squared minus t plus 1. We're going to say that this is equal to t squared minus t plus a quarter, and then plus 3/4. Now, why would we do this? Well, if we look at just this part is actually t minus 1/2 squared. Right, that's all very cool. And then so now what we have here is a square plus another number, and the reciprocal of that, and we're integrating. Now, this should remind you of the arctangent, and I have a idea that will make my whiteboard look slightly better. I'm going to make this blue, just so it looks different. Even though this marker is wearing off. So we have x equals to arctangent t, and then dx is equal to t squared plus 1 dt. That way, the final screenshot would be a little bit more aesthetically pleasing. Anyway, so this is what we have right now, and we're just gonna plug that in. I don't think we're gonna be needing this anymore. And by the way, this is pretty easy. You just gotta find the right square with the coefficients of t squared and t like this, and then add those on, and then add the remaining. So, I mean, it's a pretty basic trick. You can kind of see where it came from. So we have here, we have an integral, 0 to infinity. And so here we have t minus 1/2 squared plus 3/4. Now what we're actually going to do, we're just going to shift the entire integral. What is that direction? That direction is left. By a half. So this would just be t, and then this would be negative 1/2 here. Remember, that's equal. And then for this one, we can write it as root 3 over 2 squared 1 over that dt. And now we can just make use of the basic arctangent. And so we would get, is that left? I keep forgetting my right and left. That direction. What direction is that? That is, yeah, that is left. Anyway, wait, that depends, because I'm not sure the direction you're looking at it, but in my world, it's left. Anyway, this thing, and we can easily take the antiderivative. It should be pretty easy to memorize. And so we would get, this is equal to, I'm actually going to write it down there because this gets in the way, 2 times the antiderivative of this, which is going to be 2 over root 3, arctangent of x times, t times this, so 2t over root 3, divided negative 1/2 infinity. Okay, all is well. This is a constant. We could just drag that out to make that 4 over root 3, and then if we plug infinity to this, this is just going to be pi over 2, and then if you plug in this, we have some other numbers. Anyway, oh my goodness. So we have here equals to 4 over root 3. If we plug in infinity to that, we would just get the arctangent of infinity, which is pi by 2, minus. And then if you plug in negative, this inside will be negative, so we're going to turn this into a plus times the arctangent of 1 over the square root of 3. Cool. This value, I am pretty sure it's pi by 3. I haven't proved it yet, and I don't want to prove it on video in case I misdo it somehow and make myself look like an idiot. But I'm going to enforce the fact that this is pi over 3. So we have pi 1/2 plus a third. What is that? That is 5 over 6. So here we have 4 pi over 3. And then what is that? That is 5 over 6. We can cancel some stuff. So this and that. This would be 3. This would be 2. And I think that's it, yeah. So this is finally equal to 10 pi over 3. And there you go, my dear lads. I think this is the solution. Now, I could be wrong with this arctangent thing here. I'll have to check it later. I'm not really sure. But if all goes well, this should be the answer to our original integral. And I think that's kind of an interesting one, because it makes heavy use of the beta function, right? We had to transform from this to this, and then this to that, and then trigonometric identity, and then Weierstrass substitution, and then unknown arctangent value to get our final solution. And I was talking about the final snapshot earlier, and yeah, so I'll just stand aside and I'll let you guys have a little screenshot, have a look. And that should be the end of today's video. So, once again, this week there's probably going to be 2 videos. You can think of it as like a sort of apology video for not uploading for so long after promising that I would do every 2 weeks. I would still try, of course, but if I get sickness again or something, don't blame me. So, that's the end for this week, and I'll see you guys in the next fortnight, if I can. See ya.